To summarize, I'm 90 years old, so I'm an old scientist. I started more than 60 years ago at École Normale in Paris, where I stayed for more than 20 years. And then, as I said, I moved. I was asked to come to Chicago. And my subject, I'm a physicist, so my PhD was on plasma effect on the sun, and then plate tectonics and many physical phenomena. From there, I moved to a very simple study of what happens in nonlinear dynamics, which means if you have a pendulum, if you oscillate a pendulum, for a small amplitude, it's a linear process, because there's a sine term, small amplitude is equal. And if you increase the amplitude, it becomes nonlinear. And then if you force the pendulum, you can have many dynamics, in fact, all the dynamics you want. This is what I did. And among that, one is called period doubling cascade. So it just tells you how nonlinearity can lead to very complex processes. And after that, I felt that for me as a physicist, biology is also a nonlinear system, which is out of equilibrium, which is dissipative, and has many of the aspects of dynamics. So that's why I went to it. And I did a lot of work on bacteria. I will show you after that one work we did. The last one I did with a postdoc before he died. And now, as an old man, I'm going into philosophy. So philosophy means if I ask any of you, what is life? Do you have an answer? Do you know what is life? Do you know what is life? Has anyone an answer what is life? So, for us, life, I'm not talking about human, I'm not talking about our species, but life is a problem, it's an unstable processes which diverge and is essentially respond to survival. All of us here, the plants, everything, the only function is survival. So there's one function for a physicist, which is like a Libchaber function, it's a survival function. Now, how do you create survival? Life did it by a very particular way, which is through self-reproduction. So, as you know, the mechanism of life is to each organ gives two, and two makes four, and four makes, which means that it is exponential, which means it's diverging, which means if we do nothing to it, life will disappear by multiplication to infinity. So the process of self-reproduction is a very complex process. We know that in industry, nobody has ever tried or succeeded to replicate the iPhone or to replicate a computer. Because logically, in order to self-reproduce something, you have to have self-reference. You must know something about the organism. And then you can self-replicate. So it's a complex process which was first introduced by von Neumann. John Neumann found a mechanism, proposed a mechanism to replicate. That mechanism needed two machines. One machine is, you need first a tape. The tape has the information, and the tape can compute. With the program of the tape, you use a constructor, and you construct the machine. At the same time, tape has to be copied. So you have a copier and you have a constructor. The constructor is all what we know how the cell multiplies. And then we also we have with DNA replication. Now this is in 45, so it's before Crick and Watson, which means that for Neumann, logically, was proposing that for any self-application, you need a code, you need a tape. It was found later that the tape is DNA, not a tape. So this is a conceptual design, but once you enter into the logic of self-replication, you enter into catastrophic logic because it's exponential. And we know that, and we know that all the catastrophe we are seeing, and global warming and everything, is due to this self-replication, which diverge. And of course, now, if we want to reduce some of the global warming, we have to reduce self-replication, which means that we have to reduce the number of children, which means that we have to reduce the population. There will be no really other ways. So now, what about this construction? How can that be done? So then we are proposing another logic. Again, we propose a language to discuss life as a cascade of machine-making machines. We know that we are machines in many ways. Our mind is a machine, our heart is a machine, and in fact, we have a machine at any length scale and any time scale, down to the atomic level. We have a machine taking proton and electron and defining energy with that. So we propose a language to discuss life, and you will find that there are two cascades. One is once you have the simplest self-reproducing machine. Now, the simplest self-reproducing machine in life is a bacteria, like E. coli. And when you look at E. coli, what is the length scale of E. coli? It's a micron. What is the time scale of E. coli, which means the reproducing time scale, is 10 to the 3 seconds, about 20 minutes, 30 minutes. So those are time scale and length scale. And then one of the cascades is how do you build E. coli? How do you construct by different machine, which will cascade and across a machine to end up by making the simplest self-reproducing machine. Now, once you have E. coli, once you have a cell, you start with organization of cells, and they make different type of development, including this one. That is the other cascade. Once you have built a self-reproducing machine, you look at all the sociology which develop humans and everything down up to. So once you put in this logic everything together, you have X and Y. X is the length scale, Y is the time scale. And the physicists, for us, that length and time are essential. And you can see that E. coli, a self-reproducing machine, is at the 10 to the minus 6 meter, which means a micron, and 10 to the 3 second, which is self-reproduction. This is the key for us of how life is constructed. Now, how do you make this? Then there is a lot of machines, and we've plotted a few of them, down to the atom, which self-reproduce, and the whole thing has to make E. coli. So I will not detail to you the mathematics which gets involved, it's just the principle. Once you have a cell, what comes is organization, development organization of the cell, up to ecology, up to the biosphere. This is another machinery system, but it's a machine system for interaction, mathematical interaction. So those are the two cascades we propose, which will eventually define how a Neumann machine can function. For this one. Okay, now, why did we were thinking of that? It comes out from Gottfried Leibniz, which around 1700 was asked the question, what is life? So Leibniz said things simple. I know how to make machines. As you might know, Leibniz made the first computers with Pascal, made a number of machines. He said, I know how to make machines, and life makes machines. So here's the way I make machines, here's the way life makes machines. What's the difference? What makes a difference? And Leibniz said it's very simple. If I take the machine I make, when I start to dismantle it, I end up with screws. I end up with dead things. But if I take life and I start to dismantle it, it will be always alive. It will be always functioning. And Leibniz said something which is extraordinary. The machine of nature are still machines, a smaller part. To infinity, he was proposing to go to the atom. So already he has this view. And it is that view that we have tried to develop, that we are trying to develop. That makes it clear. So there are two cascades. You have the first step, the main step, what separates life from everything else is self-reproduction. And self-reproduction has been chosen for survival. Because if you self-reproduce, you can always make enough species so that there will be always some which will survive. So that is a logic that life chooses, and no other system. We go up to the galaxy, we go to the physical world. Physics never works with instability. Life is built on an instability. And that instability, you start now to realize it, it's global warming, the result of that instability. Because by multiplying all the time, we destroy everything. So the idea came from Leibniz. Okay, so he talks about machine. So if you ask me what is a machine is just an object that transforms a physical system non-randomly to perform a definite function. A machine injects global order into a universe driving towards entropy. The machine is an object which will fight entropy. And what we are proposing is that all of life is a millions cascade of machines. And each machine self-reproduces and they interact with each other. So, all of that, you need to, because this is the beginning of a book we're writing, you have to understand where all the ideas like this came from. They didn't come from biology. It come not from physics, it comes from mathematics. The first one is Gödel. I don't know if you know anything about Gödel. You certainly know that he has solved some fundamental mathematical question. But among other things, what Gödel was showing is what's called Gödel number. If you have an infinite library of books, Gödel shows you that all of the books could be written in one number, and from that number, you can recover each book one after the other. That was a major development, because it tells you that what life does with DNA is the same idea. It's a huge library, which is localized. And in the case of Gödel, it's localized in big number. Now, this Gödel number is, in a way, the precursor of the possibility of DNA. And of course, the next one was Turing 39, who shows that if you have a tape, you can compute. And the Turing machine is a little object which computes. That may remind you of some aspect of gene expression. So you see, the mathematicians in the 30s were putting some of the background. So that's what we take a look. Okay, I just wanted to tell you a little of what I'm doing now. So it's just to try to develop some aspect in the language of life, how to define that. So, the question, one question. say you don't understand, say you don't see the point.
No, I not appreciated that. Can you go back to the scale?
What?
Can you go back to the scale?
Yeah.
So what? I know you told me this, but yeah, here. So what drives the T equals L to the 4 dependence to T?
Here are all the type of possible machines.
No, what is the difference in the scale?
The scale, the K is the length to the fourth time.
Yeah, but how did it cross over? What is
Now, how wide we get that, that's a big computation, which I cannot develop here. Same way as the other one, where you take you, and you start to make your organization. We start to make your university organization. We start to make Swiss organization. We start to, all that is this. Once you have a self-reproducing machine, it starts to multiply and start to create organization. Those are information organization, while those are physical life organization machine. Okay? It's that you see the two steps. Now, of course, for example, if you ask me where deep learning is, somewhere here. Inside this organization species, because what we do, what bacteria do is similar. I mean, one can do many plays with bacteria. Bacteria construct cities, bacteria does everything. So don't be too pretentious about our possibilities, they are extremely limited. Question? Any question?
So my question is like, so this graph maybe shows that as long as bigger the systems become, the scales linearly with time, let's say. That organization only comes like linearly with time. So why there is a dynamic shift, like why it becomes slower when the length scales?
It depends on the size. As you can see, for very small size at the atomic level, it's 10 to minus 12 seconds.
Yeah.
Because it's
But
very
it's much
fast.
fast.
It's very fast. So as you go to bigger, the time gets bigger. And then you can up to the first self-reproducing machine total, which means E. coli, the time scale is 10 to the 3 seconds. What's that? That's the reproducing. Every time, you understand. The only thing about life is that life self-reproduce. If you take that out, there's nothing special about life. And why does it self-reproduce? Because normally life should disappear. So you need a mechanism to make it alive.
Yeah.
And why is it just on the Earth and nowhere else? So the solution which has been found is with self-reproduction, we can build on instabilities and regulate those instabilities.
But why it becomes slower, like, you know, like
What?
why it becomes slower, like after self-reproduction?
Because after that, it's not anymore machines making machines.
Yeah.
It's organization.
Yeah.
So it's an information process. It's completely different. What you do between yourself, you don't make machines, you interact.
Yeah.
And say that is the scale which goes in this time. So you have to understand. The important point is the bacteria. It's length scale, it's time scale. From that, you can see how it is built, and then what bacteria do together. It's very different. What is built is a physical process. What they do together is an information process. I don't want to make an analogy with what we know now in Israel, but you can see the two processes is there too. There is an information process and there is also a physical process. Okay, so this is what I wanted to tell you about what we are trying.
About this macro cascade time scale.
What?
The macro cascade time scale, you put the time is proportional to the length. But
No, it's always the same thing.
But one can argue that it should be
But
like diffusion goes slower.
if you keep going in building, from the bacteria to organism, then the cancer will continue. But what we look here is what is the most elementary, simple self-reproducing machine. That is the bacteria. So we take the bacteria as the center. And from that we look how do you build one. And then how do bacteria organize themselves to do things. I could go up and go to human, whereas scale will not be micron, it will be the reproduction time for human. So it's much longer. But here the idea is that we are trying to build biology step one. Starting from the atom, what kind of machine are used, atomically, and they are, to create some ATP, and then how you build up, and at the end you have enough machine which together will make the self-reproduction that Feynman needs not. Because Feynman was saying, to build this constructor, you need 45 elements. And he said, I don't know what to do with it. I don't know how to make it. So here we are proposing one language to talk about it, the language of machines. Just machines. Which means that every step, every dimension in us is a machine. And the beauty of life is that we have a machine at the atomic level. As physicists, we are unable to make machine at the atomic level. Life did it.
We come to another question.
Yes, question in the very beginning is that so life is about survival and it's about self-replication.
Yes. Self-replication to survival.
To survival. But then you said it's a very particular system. So do you think any other system could be possible to have a dynamic unstable?
Yes, we can do.
It's not the only solution.
No, it's the simplest. In a way, the bacteria is one of the simplest organisms and proteins.
No, my question is, if you would create life new, let's say, on Earth, would it be possible theoretically to have it different?
Yes, of course. Because our life is based on what I call the 678 solution, which means carbon, nitrogen, oxygen, and water. So the life we describe is on water. I take from the man, I put from the man in salty water. What comes out? What comes out is what we have now. But it could be done differently in other fluid. It could be done eventually. If you find a mechanism to build self-reproduction, you could do it in many different systems. I'm describing what we have now. Salty water is essentially carbon as the fourth element, oxygen for energy, and nitrogen between for production. So I developed some ideas about this 678 solution. But that's what I'm describing.
There was always a discussion whether it could be also be built on silicon long before AI and long before computers.
We would eventually think of doing it not in water, not with the simplest atomic element, because those are not the simple, not the simplest. Never been tried. Maybe chemists should try to do another way.
There
So-
was a question here.
Again, my logic is only a logic in water with atomic element, what we use.
I just have a simple question about the time scale of machines that maybe are non-information based, like non-life. So the simple machines is like T to the L to the 4, and then the information based is like T to L. But what about larger machines like geology
Larger
or space things? Would they follow L to the 4
No,
or L?
because they are not biological. They are not self-reproduce.
So
Geology doesn't self-reproduce. When I studied, which I did 60 years ago, the waves on the sun, while the sun was hot, has nothing to do. There is no self-reproduction. There is nowhere self-reproduction, only in life. And that is the main thing you should keep in mind. And this is why now, if we want to solve the catastrophe where we are going, is by playing with self-reproduction. People are saying change the energy you use, change this, change that. I don't think this will work. It cannot. But if you stop making children for a while and bring 8 billion to 1 billion, we will help the problem much more.
Sorry, I have a question. So, what is the spore, and why is it so? Why does it have such a long time scale compared to everything else?
It's the way it was made. Because
Sorry.
how can you make a machine which self-reproduce? If you ask the question, for example, us, as you know, to make a machine which self-reproduce, we need extraordinarily complex processes. And with productivity, which naturally is very poor in earlier time. You know, 1 woman out of 3 were dying at birth. That was a logical thing in Neolithic time. So this is a mechanism which can produce one of the simplest self-reproducing machines, bacteria. So, and how can you build a logic for that? Okay, now talking about bacteria, I don't want to continue in that because it will involve more complications. So I will stop here. We take from the land concept. We take salted water. We add a few of the atomic elements. How can we build the first simplest one is a bacteria. How do we make that? What is the scaling needed for that? Once we have bacteria plays the same game. There are, plenty of mechanisms that bacteria use. They create houses, they move, they have organization, they have everything here. So that's trying to define what you need to construct. So now I wanted to show you last experiment we did 5 years ago, playing with the Earth. I want to amuse you with one bacteria, which is an important one in the Earth. So there, the work is done essentially by Alex Petrov, who is now at Prague University. What we want to know, we want to take mud and study the bacteria in the mud, because all those bacteria will define all the agriculture. So where do we take our mud? We need to take mud because there's no trees, nothing, just pure mud. We take it near Boston, at Woodford. And so it's life at low Reynolds number. I don't have to define Reynolds and Beckley number. Just to tell you is that mud is a porous medium. Because it's a porous medium, there cannot be flow, the diffusion. And I will show you that some bacteria are able to organize themselves to pump material without moving. So let me go on. So that should amuse you. So what we do, we take mud, we bring it to the lab, we mix it, and we put it with water, as it is in the mud, and with photons. High energy and low energy photons. That's it. After 10 days, what you start to see happening is this. They just happen naturally by diffusion. And there are hundreds of different types of bacteria. So the band up there is due to cyanobacteria. Cyanobacteria, they pump UV light. And because they use UV light, they have enough energy to break water. So cyanobacteria in particular, produce oxygen. In case you didn't know, more than 2 billion years ago, there was not enough oxygen on the Earth. Then the cyanobacteria came out, and they produce a major part of the oxygen. So they are at the origin of our life. Those are the cyanobacteria. So they use UV. So what you have here is the mud in a gradient of photons, and since you have cyanobacteria, you start to build a gradient of oxygen. The oxygen produced by the cyanobacteria. So then, infrared light, you have a purple sulfur bacteria, which comes in to get what is left. UV light is taken by cyanobacteria, and then infrared is taken by purple sulfur bacteria. After that, you have no more photon, but you have oxygen. Oxygen created by the cyanobacteria. And there, we have two types of bacteria. This band you see here is a sulfur oxidating bacteria. They use SH2 and they oxidize it. So they're producing H2S. So SSO4. They take H2S, oxidize it, makes SO4. So in doing that, they are producers. So they produce sugar, carbohydrate. Those are the producing bacteria. And so to summarize, those, which is the one I will show you many things about, are taking SH2. You know that sulfur comes after oxygen in the column, the same way as you have H2O, you have H2S. They oxidize it and make SO4. Now what happens then? Those bacteria, the sulfur-reducing bacteria, they take SO4 and reduce it to H2S. So you have an oscillation here between H2S diffusing here, H2S making SO4 here, which diffuse. So it's a coupling between this sulfur oxidating, sulfur reducing. As now the sulfur reducing bacteria, in order to reduce, they need the sugar which is produced by the other one. So those are the third is the producer, the second is a consumer. And as you know, in our society, we are producers and consumers. We are consumer and some agriculture is producing. Here's the same thing, but it's two groups. Those, it's called theophyllia majors, and this is the sulfur-reducing bacteria, which use as a source of energy the sugar which is produced here to reduce SO4 and make H2S. This thing is a lot looked, and there are many of looked like that in bacteria world. So now we play as a physicist. We take theory of majors. Why? Because this bacteria is the fastest bacteria. It can move almost millimeters per second. It has 300 flagella. So it's a huge machine of motion. Okay. So here I summarize. Mud, the medium is porous, does not allow flowing. So no metals and moving slow. The main transport mechanism is diffusion. That's a porous medium. There are many control parameters responsible. So I describe you what energy photon does, what infrared photon does, what oxygen does, and so on. So how do we do that? How do we take it? So we extract, we purify this theophyllia majors, which is a producer, which produces sugar by burning H2S from the oxygen which came from the cyanobacteria. It lives in water, so far and so on. It's the fastest moving bacteria. It has about 400 flagella. It can form tissue veil, it can attach, and I will show you a few things we did. Okay, so this is what I was saying, toxicity is tuned to sulfur. Is a producer, below it in the mud, sulfur-reducing bacteria transform the sulfur back into such. So it's a couple. It's a pair which work together, producer-consumer. This is amazing bacteria. This bacteria is about 6 to 7 microns. It's a big bacteria, and it has a lot of flagella, as I say, 400.
So flagellas are those, right?
Also, what?
Those are flagellas, those small things poking out in the picture.
No. This was just a picture.
That's it.
Here I show you how it divides. But also you have to remember that this bacteria has sulfur crystals. In order that it used such so it has 12 crystals of sulfur in itself, which is using. Now, this is the bacteria when it is pleasant. And is divided. Divided into two, it's pleasant, and it keeps moving. Now, this is theolinium. What you see here are sulfur crystals. It is pleasant, so I will show you how 400 flagella induce motion. It moves fast. You see how it pumps? It's a fantastic pump. When it's desert, just move. All the flagella pump water out. So it's a fantastic pump. And this is what we use. Because in this case, in what we do, the interaction between all the T-helium will not be by chemical means, but by flow. And you can see how effective this bacteria is in pumping. This is about 5 microns.
Is this so it can feed itself? So why is it pumping the water so that it can feed itself to get it?
It will organize itself, pump water, and as it pumps water, it pumps all the material. That's what I call large Becquerel number. So it can pump material without moving, being fixed, which is what we should do.
But like this is very fluid system, right? So this is like water. But the mud overall is a very viscous thing, right?
Yes.
So how does it work in water in the mud where it's which like much denser, much viscous?
Diffuse. Diffuse. The bacteria are microns. The porous medium is such that in the mud it can diffuse.
It just moves around very fast.
Yes, but also in nature it will be in water also. So now all those bacteria they can make a tissue and just feather, which means they will all pump, and all together they will pump a lot of water. This is in nature how they work. This is what we call high Becquerel number, which means the bacteria doesn't have to move to choose for food. It attracts food by the flow. Now moving, rotating, as you've seen on the feather, and there's a huge amount of flow. And so they, by being fixed in a veil, they can get all the nutrients without having to move. So there's a special type. And sometimes in the mud, when you see a muddy place, where you see a veil, sometimes it's this veil. And that is a particularity of what those bacteria use. By getting together the collective motion, which lead to large Becquerel about 50, which is a very efficient way of pumping by using all the flagella.
But then it is just to it is just to bring the stuff close to them. Then how do they infiltrate? Like how do they fit inside their body?
What, how do they?
Like this is just a mechanism to bring the stuff close to them.
Yes, I mean, what they want is normally bacteria go and move toward food.
Yeah.
This bacteria, they organize by making a sheet.
Yeah.
And then the sheet pumps, because they are such fantastic pumpers, that the food comes.
Yeah, but then how is it means for their survival they really have to work together as a group?
No, they can also be individual. It depends on the surrounding. It depends. In the mud, no. But when they are in contact with water, they make a sheet. And in the sheet, they all connect, attach, and they pump. This is the one we saw. It's the one which we found in fact, even in Zurich, maybe in place where you have some sandy things and some water is really dirty. Sometimes it's that, no. Okay, now, the discovery we made that is to produce the first type of crystals of bacteria. So, what happens? If you take those bacteria into the fluid between two glass plates, they move. When they hit the glass plate, they pump. They are blocked, but they pump. So they bring fluid around. You follow? So if another bacteria in this bag is attracted. And then, as you have seen, all those bacteria rotate because every flagellum rotates. So they start to rotate to each other, which you will see. So this is the pattern. Bacteria comes here, is blocked by the glass plate, but the 400 flagellum work, so they pump water. So if you have a bacteria here, positioned here, it will be attracted. So there will be a two-dimension dynamic of all the bacteria who are stuck. Okay. This is what we make. Crystals. Each element here is a bacteria. It's one of the trillium. If you see different color, it depends on the sulfur crystals. Sulfur crystals make different position. But then, this is what happens. If bacteria can't stick or not stick, this will depend on crystal position. Because if a bacteria algae is surrounded by many bacteria, it's stabilized. If it's surrounded by a few, it can evaporate. So this is the kind of thing you see. And now I will show you some very amusing things which look like science fiction. Now, this is a sheet for the bacteria. They all rotate, and they all rotate in the same direction. They all do the same thing. You can watch the all turn in the same direction and synchronous. And then the whole crystals start to move. It's a pumping of all. This is a small crystallite. And then they will show you what happens. It's crystal physics. If you look here, you see what this interaction, but you see also the whole thing starts to move, because each crystal moves. Okay, so we can demonstrate that the rotation depends on the size of the crystal. Bigger crystal rotate more. So we have developed a crystal, 2D crystal of bacteria, which are rotating crystals. And you see always the same thing with crystal. If it is faceted, it's stable. If it's not faceted, it's unstable. slowly they will end up by being faceted, and when they are faceted, they don't lose material like that. This is stable now. It's no facet. So that's
What determines the polarity of rotation?
everything you see are out of bacteria.
No, but what determines the rotation, the direction of rotation?
No, they interact by the flow. As I told you, one comes, create a flow, which attracts the other one. So everything you see is that.
No, but in one of the videos, sometimes the bacteria was rotating in the other direction and then it leaves.
So they can leave. It depends on how many neighbors. You see, this one has two neighbors, it's stable. If there is one here to be stable because it has only one neighbor. So it's a crystal problem. Here you see faceted crystals. That's what crystals are. They facet for the same reason. So there is a mathematics for that, which I will not develop, H number. But if you have an instability, moving on one, it brings to a lot of complexity. So we developed the mathematics of this problem. And now you will see a few surprising local dynamics. And they are small, you see, they rotate easily. And again, binding and binding. And, okay, now you see the formation of a pair. And then start working. Because of the effect of the flow of each one. Now, I'll show you other amazing things. Look at that. This is not a simulation. This is reality. All those flow end up by making those kind of dynamics. So everything I described to you has nothing to do with chemistry. It has all to do with flow and flow interaction. This is another one showing how it creates itself. So, I just showed you a very peculiar bacteria, which is known and famous because it's the fastest known. And it's fastest known because it has 400 flagellum. Plays a big role in the Earth. And because of that, we played as physicists. When I put them between two glass plates, I impose a two-dimension. Because the bacteria coming here stays here, to that move, and then attracts nearby, and make crystal, and the crystal rotate, and you can have all those dynamics. So we invented the first type of rotating crystals with the bacteria. But they play a dominant role in the Earth.
So they don't actually touch, right?
What?
They don't touch each other, right?
No.
They're just very close and then...
Yes. Because
Like,
it's funny, because even the 400 flagellum don't mix up.
okay.
You
Yeah.
know, you could wonder, no, they keep at no distance and then they do all these dynamics, which is an amazing dynamics. It surprised everybody, like, looks like simulation.
But did you measure the distance between two bacteria?
Yeah.
Like how far they sit?
When they go at some distance, which is about the size of the bacteria distance. The bacteria is about 5 micron, and they hit a 5 micron each other. Then the flagellum function, and then they start to create the flow, and each flow interacts with the other flow, and each one is rotating. So they make this. It's the first type of bacteria interacting by non-chemical means. No protein expression, nothing of that, just flow. Because it's a particular bacteria which moves extremely fast.
But you were saying that you have tested it, that there is no other mechanism of interaction.
I was not found. But as soon as they get close together, the flow is so enormous. You see one bacteria together, the flow, we can pump. It's an enormous pump.
One question.
Remember, do remember,
So let's say we have a bacteria which is rotating, right?
remember that. Remember that. This is extraordinarily amazing. Look at the speed of rotation and how it can pump from long distance, far away from itself. It's a magnificent pump. Those 400 flagellum. And somehow the 400 flagellum don't inhibit each other.
How it's rotating? Actually, I'm confused.
What
Is it like this?
other material? It's also material, which it's material.
I mean, the cell itself. how
It's
does
in the
it-
fluid. So what it is, here we wanted to show only that bacteria is tethered here by a filament which is attached to the boundary.
So the right side and left side flagella are working differently? Is it like this? Or it's not rotating?
I don't understand the question.
Is it it's not rotating, is it?
It has to rotate because it's flagellum rotates.
But then if it's rotating, it should be like this.
Yes. And then if it's tethered, it's blocked, so it can only rotate on itself. It has a filament which is attached to the boundary. You know, like some E. coli, when they develop tethered, they develop some disease. Here it's bacteria, it is tethered.
Splitting is vortex.
So for us, this was the most amazing image of what this bacteria is doing. There are many other things which are not
I have a question.
okay, now it's blocked. Fine, it's blocked. So I finished by showing you one bacteria. My associate at Clark University is studying all the bacteria. And there are magnetic bacteria. There are infinite number of different possibilities of bacteria in the Earth.
Did you try to measure the speed of rotation?
We can measure it. Yes. In fact, with the scaling, depending on the site.
But is it dependent on the material that they are suspended in?
No,
No?
on the fluid.
Yeah, the fluid.
The fluid is water.
Yeah, it depends
So
on the
dirty
source.
water. We have not done it in other fluid and water.
Slower, no?
It's just water. Dirty water, but water.
One question is that when you have this self-organization in these forming these crystals, right?
Yes.
And then this crystal rotates by itself. And of course you were saying that the bacteria is only rotating on itself.
Yes, and this one by rotating
And-
makes it also rotate, and you have the free surface.
Yeah, exactly.
That's how the system,
Yeah,
that's how it scales.
yeah,
So we have very clear scaling.
yeah. So now the question is that let's say when it's rotating, right? Every bacteria has to adjust to a certain speed, or let's say a certain beating frequency or something.
Because of interaction.
Well, because of interaction.
So there is a friction, which automatically. So you can write the equation.
It's
In
all
the crystal.
It's all automatic. Right?
But the flagellum, they flagellum.
They're just the same.
But they can be friction. And in fact, we are amazed that so many bacteria interact so well with the 400 flagellum not getting mixed up. They check the distance. In a way, they do everything very elegantly. They don't have to do calculation. Naturally. So this is one. Just to tell you that the Earth is an extraordinary wealth of different types of bacteria.
But then what is the purpose of this study? Just like find different bacteria and
In my case, it was just playing as a physicist. When I saw a bacteria which has such efficiency, I immediately imagined that I can make crystals and I can rotate. Just find a way. But it's two gas split, which is not what exists in nature. So there, I created two-dimensional crystal, and that's the play of physics. I wanted to show you just to amuse you, because the first part is too abstract.
Okay, just to add for him, it was more plain.
No, I would like to
Really,
answer question.
the soil physicists and soil biologists. In fact, this is what happens, the stratification of different bacteria is what gives rise to the quality of the soil. Because if they can actually go into different distances, because they can actually then absorb what he showed, the UV light and other types of radiation. That's how you have a gradient of bacterial system that makes your soil healthy for plantation. Or if these gradients are lost, is when you don't have proper.
No, I didn't tell you how you make the
So for him, it's more games, but there are really, the bedrock is
Sure,
actually
you make
very,
the-
very serious.
It allows the bacteria to stay fixed in the veil and the veil pumps. So, for the Petri number, which is VD over the diffusivity, becomes very, very large. And then they get the food. They don't have to look at it. The food comes to them. So that's what they do. In fact, I'm sure somewhere in Zurich, if you mud, the dirty mud, some of the bacteria will appear.
So why do they organize themselves so low in the mud, in the soil table, right? So first there are bacteria which are more like oxygen producing, and then you have on the third level you have these type of bacteria which are these pumps. So why they organize themselves so low?
Because they need oxygen.
I see.
And the oxygen comes from the cyanobacteria.
Oh, I see.
We have not realized yet that we will not be around if cyanobacteria didn't exist. We are around, we are the only bacteria which can break high energy photons. And because it's high enough energy, they can break water and create oxygen. So once all the photons that we absorb, what remains is oxygen produced by the cyanobacteria.
Yeah.
It organizes. And then those ones take this oxygen, burn H2S to make SO4. And the one below does the opposite. Eat the sugar created by the cyanobacteria and reproduce the H2S. So they work together. Producer, consumer. It's us. We are consumer. We go to shops with our producers. So this is part of a fantastic story of the man between the earth. And it is this earth which will help to develop food and to do things. So it's important now. Rockefeller, one of my closest friends, works only, he has given up everything and works only on plants. How do plants interact in order to produce the best food? Usually, the way agriculture does is to have two types of plants and look at the interaction. But in fact, what you would like is to put different types of plants and see how to optimize. This becomes a more complex problem. And that's what he's working on. Because the same way as we talk about deep learning, Africa is starving. And starvation will develop. So it's important to do the study.
I have a question.
Yes.
I'm just not quite sure how to connect this interesting experiment with the first part of your presentation. So.
Again.
Just how do you connect these experiments with the first part of your
No, we don't.
presentation? You don't. Okay.
It's two different worlds.
Okay.
This one is a world of nature. How does plants develop? How does mud develop?
Yeah.
The other one is what I'm doing now. Now I'm an old man, so I can do philosophy, and I don't have a lab anymore, so I cannot play games.
Yeah.
Because here I showed you one game, but on my life I played many games.
Okay.
Producing condensed matter physics in biology, different things. No, but there's no connection.
Maybe there could be, or-
Otherwise, then I think they are both important.
Yeah.
One, because it's about need. If we want biology to end up being a science, which it is not yet, it has to be abstract. There is no science without abstraction. In biology, there is no abstraction. So we have to start to develop some abstraction.
but maybe you could abstract this the way that the bacteria
Well,
is
yes,
arranging
yes,
in a
That's
pattern,
what
right?
my collaborator does.
Yeah, yeah, okay.
Yes. So there is no connection unless the fact that many biologists who start to think about how the species will survive its food. Because you know that the Earth has a very thin layer of sand, very thin, which is taken out. So there is a problem of food, more and more. So that is an important subject.
Mhm.
Well, what I presented at the beginning is more philosophy. Main question, one aspect biology, is to think deeply about what you want to do. One of the most famous biologists used to say that before doing anything in biology, it takes 6 months to think about the logic of what you will be doing. Does it fit? Does it work? Because otherwise you will end up to be in a direction which will have no future. So biology, more than many other disciplines, needs to think logically a lot. So what's the future? For me, what I present to you is two futures. One is the theory, which is something. The other one is to try to answer problem, people problems, civilization problems, which means essentially what global warming will do and is doing, and will do more and more, and how to act on this level. It will develop a lot. Right now, nobody is interested in plant biology, which to me is absolute madness. In 10 years, it will be one of the main subjects, because we need to feed people. And feeding people will become a very severe question. So you have to think and decide what direction you want to take.
So what is the solution?
What?
What is the solution? How to feed?
I think to me, we have to look at everything the global warming will introduce. And clearly, the response of biology will be essential in many aspects. You have to think about that. For the first part, it's something else, is that when I started, which was long time, 50 years ago, I thought that we physicists will come and help understand some aspect of biology, because we felt the biologists are too descriptive. Everything is descriptive. Well, we have not succeeded. But still, the problem remains. Biology has to become a science. And in order for any science to become a science, it has to be able to abstract. So, this is a little effort in what we are trying to do. Chemist here, I'll tell you historical part. There was a Frenchman named Lavoisier who made a revolution in chemistry in 1780 something. But the first thing he did was to write a book called Nomenclature Chimique, how to define the word in chemistry. And from that, he developed chemistry. Biology has not reached that level. You have to develop the language. What is the language of biology? How precise is it? And from that, start to develop. It will come. It's slowly coming. With DNA, genome, everything started. And step by step, you can see it coming. For example, I know that when I came to Rockefeller, the biologists were saying, oh my God, another philosopher. That was me. And now they're looking to a lot of physicists. So it's shifting. And you have to think hard. And not fall because you're there to do what they say. Is there a polymer which can have all the information? When mathematicians have demonstrated that long time before, that was Gödel number. You know, if you take an infinite library of books, Gödel transforms it into one number, and from that number, he reconstitutes the whole thing. In a way, this is what DNA is doing. So it's important, the same way as gene expression. Mathematicians have shown that the smallest machine they can make, Turing machine, has some of what you see. It has a tape, and it has a little machine running on the tape and computing. This leads to universal computation. So it will be very important for biology to realize what mathematicians have done. Because they are the one who create now what you're using. Yes.
So you mentioned for something to be a science for you, we need to be able to go to abstraction, right?
Yes.
So very concretely, what would be your advice for us who are biologists, or in my case even a psychologist, to go in that direction very concretely?
It's coming. For example, just the genome was a huge change in biology, affecting everything. And that is a game of numbers. And the fact that all those numbers are localized in a small polymer, which is DNA, is again the beginning of abstraction. What we are saying is that all of that, more or less abstractly, was proposed already in the 30s by three persons. Gödel, von Neumann, for central production, and the machine, the fact that it's a universal computation. You all use your iPhone, you all use your computer. This is Turing. You are not realizing that all your work, all your time, is not doing science, is playing with Turing machines. And the young generation more and more. So we better to realize that it's not two different worlds. It's not. Biology slowly is coming as an abstract science. It's a complex one, so one has to develop this complexity. But it's, to me, as a physicist, you know, chemistry became a science when it abstracted. Physics became a science when Galileo could abstract. Biology will have to be the same at some point. But it might take time, because right now you have so many things to do.
But would you advise that we learn, for instance, mathematics or physics to get closer to this concretely?
I think it would not be bad. I think to start to think abstractly, might you allow how is it that you're becoming an automat, depending on your iPhone? Why is it that you become an automat depending on your computer? Just understanding what mathematics is making you would be useful, because it would allow you to liberate from ourselves.
And are you aware, so you spoke a lot about von Neumann. He's also one of the fathers of game theory, right?
Yes.
In more
Yes.
of a psychology.
For the same,
economics.
it was more for him one way of trying to answer the problems of constructor by game theory. Yes, I mean, we have there three persons revolutionized everything, in particular society. So the point is, you are using all of that result, not realizing. It would be better to realize. For example, some of you have heard about the revolution that Gödel introduced in mathematics, showing that in mathematics there are something you cannot prove. The same Gödel invented this Gödel numbering, and when you look at it, you say, my God, but this is a general. Just a Gödel number. It's remarkable, you know, by playing little games in mathematics, he can transform an infinite library in one number. But more than that, he takes that number and reconstructs the library. Step by step. So in some way you can see it's far from DNA, but not that far. And that was done much before. Much before.
Does anybody not agree with him? That's also good.
Well, I can see all those machines, everything.
You don't have to agree with everything he says, right?
It's all shooting.
Any other?
If I share something non-agreeing. So when I talk to physicists, I mean, we are at a physics institute, as well. They always criticize biologists for exactly the same reason. We are not understanding our systems well enough, which is correct, I agree with you. But my answer is always, the systems are so infinitively more complex than your systems, it's not possible. So when I think about one of the last Nobel Prizes in physicists was on glass, remember, on the transformation? And it was in the Nobel laureate speech, was a lot about this is a complex system, and it's a complex system for physicists.
Yes,
I agree. But for biologists, it's still a very simple system.
But for biologists, they don't study the system, they study the software.
I know, yeah, but I think
look at
structural biologists, they are very much understanding their systems, very atomic. But again, when we all believe when we understand structure, we understand function. But now we understand that even if we have the structure, the system is so complex, it's really difficult to get the function. So
one has to push in that direction.
Yes.
And not give up by saying it's too complex. It's not true.
I don't know. I'm not a mathematician.
Mathematicians have shown conceptually that there is not so much surprise. When biologists come and say, look, this is surprising, we say, no, not true. Not true. Turing and the other end from them create much bigger surprise. And in particular, there are the roots of biology.
I agree with you.
As you know, self-reproduction is an essential part.
Yes.
Essential.
Yes.
Without it, there is no biology. So one has to keep doing. And for example, I'm writing a book on those concepts, possibility concept, and see how there's some possible connection.
But if you go to the details of biological systems, self-reproduction is already so complicated that it's really difficult to perceive how it evolved.
But we knew all that with chaotic state. I was part of the people who created those chaotic phenomena that in chaos, the stream of order, the stream of logic, it's complicated. So we've seen that in physics already.
That's true, but
So,
a little.
Agree. And because it will be an essential subject.
No.
And the biologists have to continue doing what they do, detail every step, but it's infinite. So there is an infinite number of biology to.
The question is, yes, I agree, there's an infinite number of biological questions you can ask and answer, but how do you get it back with
This is
a
what
logical
system.
in a logical
To say like a cascade of machines. There are the infinite cascade of machines. One uses machine. I showed you even there is a bacteria. There is the one who uses oxygen, produce sugar, the one who uses sugar. And they play.
With bacteria, actually, that's another thing where when you speak about disagreement, where I don't think bacteria are simple.
You don't think?
Bacteria are simple.
No.
I think from a chemical perspective, they're much more complex than we are.
Oh no, not I think disagree.
Yeah, you have these complex chemical systems. For example, in mud, it's not just one bacteria species, many, but the system is more complex.
Well, what are we? In first order, we are bacteria. We have more bacteria than human cells.
Exactly. Yes.
So you cannot say we are simpler.
Yes. Okay.
Because we
Okay.
are
When you
big
take out,
from
yes,
bacteria.
I agree.
We are essentially big from bacteria.
Okay, I agree.
Why has physics been so successful? Because every physics student starts with a very heavy load of mathematics. And all our exam, all our selection is mathematics. And once you can do that, that's what has made physics a successful science, which control everything. I mean, as you know, part of the physical world. We can go to the moon, we can go to Saturn, we can explore atom bombs, we can do so many things as physicists. But it's all based on, so I would consider that the study in biology is too much only biology, with no foundation. We should have some math and physics foundation, and then biology. But you cannot only work with biology. You will lose, you will not understand things are coming, because there is a mixing now coming. So that's the only thing I say. It will not, it should, in the long term, help you, because there will be a lot of changes. Already, you know that biology is far from being perfect. To give you one example where how far was involved, all biology textbook tells you that the immune system cannot recognize cancer. Textbook, all the textbooks of all the world for the last 100 years. We know now it's completely wrong. The immune system does recognize cancer, but there is a switch where the system is considered fine. It's okay, it's no problem. So now that they know that, they play with the switch, and as you know, it's one of the rare successful cancer treatments. But it's based on 100 years of completely wrong knowledge. So how much is wrong, I don't know. But several things came with regulation. First there was only DNA, then histone came, then RNA, small RNA came. As you can see, things change. Okay, that's my advice. I started my life as a specialist of semiconductor.
Yeah, true.
So without NVDA, which means without physics, without
No, and my question is more like, so what's next? Like, what do you think is next in this pipeline? You know, like as information, laws, and then what could be more here that could maybe make a reasonably abstract system, let's say, to make biology a science. Let's say you have a way to assimilate large amount of data. Maybe that's where deep learning would help. You have a way. You have some basic like physical laws in which biological systems behave. And then what next? Maybe can you like so that you know also towards like what should we do next?
This is a very hard question.
Yeah.
The only thing I can say is that the education should be more rigorous. The education in biology is too much only biology. And that is another thing. Because it will not allow you to follow what comes out. Because deep learning is one step, it's a technical step. Now, the physicists will develop other subsystems.
Yeah.
And right now, one thing which is clear is that global warming imposes a number of things. There will be problem of agriculture, there will be physical problem with the climate. It imposes to studies. And unfortunately in biology today, it's not fashion. Plant biology is not fashionable. And there is a very small effort, which to me is ridiculous. Because it will soon become a very serious question, because you need to be fed. The same with self-reproduction. Now people realize that self-reproduction is essential. That if we are destroying the earth, it's thanks to self-reproduction. That terrible mechanism is terrifying. It will last forever. So one has to deal with that. So for example, for me, one of the great politicians of the century is Mao Zedong. not for communism, but because he imposed one child per family. That was a necessity, firstly. Absolutely necessary. To allow this explosion to reduce. And biology has things to say about it. Now, you are working on something different. Your main aim is to help detect disease.
Yeah.
And for that, you use one receptor, which in principle is sensitive to anything because it's DNA and fluid with it. How can you do it? That's all what you're doing, and that's very powerful eventually if you are able to do it. Because all disease have a mark on DNA and the nucleus automatically. How much can you really detect? How much can you use modern mathematics and physics to help you? What you are trying to do now is a deep learning mechanism. So I understand the problem you are facing. It's up to you to show that yes, you can. Yes. What's the question?
Just if you were able to start a lab today, but with all the knowledge that you accumulated during the decades, what would you study?
Today,
Today,
I will have two levels. One level is what does nature, what does society need? Because today, society is a scientific society. Today, you're all robots, whether you like it or not. And so in that scientific society, it has to survive. The only way to survive is to face some of the problems the society has, which means food and weather conditions. That's one thing. The other step is that biology, like any other science, has to become abstract. So I would like to push this abstraction. That's what I would do. That's what I always did. Why did I come to biology? To bring physics into biology, to show that, for example, in the bacteria I showed you, when I present to biology, so you're lying, it's all chemical interaction, because in biology it has to be chemical interaction. Say no, I give you an example where it's physical interaction. It exists also, so don't be stubborn like that. And me, that's what I will do in both directions. One is essential. There are other directions, of course, but that's not for biology, which is energy. We really, as physicists, we have to face the problem of energy. As physicists, so I'm not talking about biology. If I ask a physicist, I will tell you that's very fundamental. You know, get rid of oil, get rid of that, develop other mechanisms for which biology does easily. As you know, biology is the most consuming energy thing in nature. You are consuming massively. That what I would do, but you know, I have too much training in math and physics, so I may not be ask him. But I do believe it's important to gather, to connect. Otherwise, you know, in biology there are infinite problems. It's the same our machines. There are millions of machines. You can take anyone. I used to play with tubuli in the microtubule. It's another machine. Microtubule can move and can interact and can separate chromosomes and it has plenty of machines. So, but they are acting also, and then it can burn. And DNA, as you know, has infinite possibility. Even in replication is not trivial. So that would be what what I would do in my mind to arthritis, not disease. Because that's medical. And that's entering a world which I found complicated.
Yeah,
Too
we discussed it, yeah.
No, complicated not because of the doctors, but because of lawyers. Complicated. You have to follow a few. If you want to be creative, never work where many people are working. Try to go in places which is not crowded. That's essential. Very far. For example, I was one of the first to study bacteria motion. How did I do it? You know, soap bubble. I took a substance, it's 2 by layer with a micron water. I injected bacteria into that. Then I had a 2-dimensional dynamic probability. So I discovered a lot of dynamics, which is now considered a classical founding paper on that. But I went to extreme cases and mixed them. Never go where it's crowded. And try to go in places which looks ridiculous, and that's your better chance. Otherwise, you will be 1 out of 1,000. In my case, it's complicated because I work on plate tectonics, I have worked on the dynamic of the stone, I work on many subjects. I even exploded atom bombs when I was young. It's a bit singular trajectory. So it's special, but I can see Shiva knows that I produced many professors, a very large number of professors, and they all finally found original ways. Original sense. So somehow I play some role in it. I give you a lot of freedom to think, a lot of freedom to go in new direction.
Thank you.